takes a long time. Derivation. Boltzmann. Then the plan today, we're going to try to cover the following 3 points. The first one is basically the preparations and raw time theory. And second is multi-layered ansatz plus what we describe as a molecule representation. And third is basically the so-called cutting operations and kind of the analysis. Okay, and then tomorrow we'll be focusing on what is left, which is this this cutting algorithm that we'll introduce at the end of this today's lecture. Okay, so let us start by starting with these backgrounds preparations. So we already know the set of the problem from last Friday's lecture, but let's briefly review it. So we have this half sphere system. We only have these collisions. Let's say we call this V1, V2, or V1 prime, V2 prime. They satisfy an elementary relation by elastic collisions. And then we have these m particles of diameter epsilon, and we're assuming this goes on grad scaling. So n times epsilon square equals, let's say, 1 in 3 dimensions, equals a constant. Here, let's take it to 1. In a hydrodynamic limit, we're going to take this guy goes to infinity, but for now, let's take it to 1. Okay. And then we are considering the distribution of these m particles, but we're not considering the whole m particle system. We're considering the distribution, the marginal distribution of the s particles. So we have this marginal s particle marginal, so Fs P Z1 Zs, so Z equals X and V. Okay, and then let's say F0, so Fs of 0, let's say it's a product of initial data. So this is a factorized initial data. And then we start with initial data, we evolve according to this half-sphere system, and we consider the time, the S particle marginals at time t. And the theorem is that those F equals F Pz or Txv solve the Boltzmann equation. P any finite time, then we have this S particle marginal. This equals a product F J. So the factorized product of the solution to Boltzmann. plus O of epsilon to the some positive power, and all these error terms are taken in the L1. L1, in action V for fixed. Okay, so this is a theorem. Okay, of course there are variants where you have the RD or the torus, T equals 3, and regarding this L1 and exactly what power you're having here, but roughly speaking, this is it. Okay, so before we start, as a warm-up, let's first discuss the physical and the intuitive idea. If you assume you have this property of chaos, basically this property of chaos, let's assume independence. Physical warm-up. Assume independence for all time. How do we get both? So this is a well-known thing, but I'm going to repeat this first of all, so that we can see the reason why we see this collision operator in Boltzmann equation here. And second is that this idea leads to the important notion of recollisions that will play a kind of key role in the subsequent proof. So let's start with this physics argument. So the idea is that we consider, we can say the S particle density, S particle marginal, but let's consider S equals 1. You can have one particle marginal, F1 of Tx and V. So F1, this is the density function of a single particle, basically the probability, single probability density that you find a particle near the position X and the velocity. Okay. And this is, if there is no collisions, then everything goes linearly. Then this thing will be transported because X is linear function of T times V. Okay, then you get a transport. No collision implies you're having linear transport, which means that the right hand side is zero. Now, if you have collisions, you're going to see non-zero thing in the right hand side, which come from collisions. But basically, you can think that this collision, you're going to have F1. Basically, there are two terms. One is a gain term minus the loss term. So these two terms, as I explained last Friday, this gain term is basically the term where you have two particles collide to get your first particle to be exact at velocity v. And the loss term is where you have a first particle at velocity v and it collides with something else and it moves away from velocity. Okay, so let's look at this term. The other term is pretty similar. Then let's say the gain term. So if you have two particles collide, let's say you want this particular velocity to be v, this other velocity, let's call it v1. Okay, and then these input velocities, v prime and v1 prime. Okay, so this term is essentially still have the integration in v1 because v1 can be arbitrarily chosen, and then the collision angle can be arbitrarily chosen. So basically you see this integral, R3 times S2 dv1 d omega, and you're having a bunch of weights, v minus v1 dot omega plus, and then you have essentially the probability density that you have this particle at velocity v prime and have this particle at velocity v1. Okay, so probability density, which is F2 of P. Let me ignore the X. Oh, please going to write X here. So X, let's say U1, X U1. This means that this probability density of two particles at position X and velocity V1, V prime, and this other particle at position X and velocity V1 prime, and they collide, gives out the particle, your first particle at position X and velocity. Okay, and you have V, sorry. Okay, and of course V prime and V1 prime, they are explicit functions of V and Vy and omega, which I'm not going to write down, but you know the collision point. Okay, so now if you assume we have this independence at all time, of course the highly non-trivial thing to justify this mathematically, but if you assume this is true, then this is basically equal to the integral R3 times let's say S2 v1 d omega times this weight. And then we have F1 of Tx v1, so v prime, F1 Tx v1. Okay, and this is exactly the gain term in the in the Boltzmann collision operator in Haussphere case. Haussphere case corresponds to this weight. Otherwise, you're having this this v prime and v1. Okay, so this is a simple argument, and of course the last term is the same. Last term is where you have this is v, this is v1, and this v prime is v1 prime. So here you just have a f1 of txv and f1 of txv1 is a v prime and v1. But you get the same. Okay, so then this equals the integral of something times. If you write, you in the convention, this write f prime is f1 prime, have a f prime, f1 prime as f1 and gv1 dO. Okay, so this is a physical kind of approach. Now, of course, the issue here is whether or not this thing indeed can be factorized into this times this. If we have factorization, that means the two particles, these two particles are kind of independent. But we know, since we have a lot of collisions happening in the whole dynamics, the particles are no longer really independent as they are kind of initially. Okay, so what's the problem here? Okay, so the observation here is that you don't need the independence of all the particles. Remember, in this formal derivation, you only need the independence of this particle and this particle, and these two particles are supposed to have a collision at this time t. So in other words, in order to justify this Boltzmann equation, we don't really need every particle to be independent. We only need essentially those particles that are involved in the collision here to be independent kind of for the time between 0 and t. You see. Okay, so this is the first observation here that two particles colliding at time t, colliding at time t, will be independent before time t. Of course, again, this is again not always true, but we need this to be true kind of up to the lower order terms. Okay, now let's see. When are two particles independent? When are they not independent? So this is very easy. Basically, if you think initially everything is independent, and now you have two particles. So let's say there is a particle here, there's a particle there. Okay, so if they have no collisions, then they are independent. But they may have collision. Let's say this number 1, this number 2. They may have collisions with other particles, like this. This number 1, they may have collision with number 3, for example, and then number 2 may have collisions with number 4. Like you draw like this, they're still independent. The time when they're not independent is when they are colliding kind of these two particles they themselves they're colliding with each other, or kind of they are colliding kind of they are connected by a sequence of collisions to each other. So let's say here, when they have colliding with each other, then they will not be independent. And in the same way, even if you have something like these 3 and 4 collide with each other in the previously, this is 3 and 4, then this means 1 and 2 will not be independent. Okay, so basically independent means non-independent means that the particles are means being connected by collisions. So this is a more general term. So 1 and 2 directly collide. So you see this time t. Okay, so the question is whether or not these particles 1 and 2 are independent before time t. So if they are colliding, they have a direct collision, then they are not independent. If they are indirectly related by sequence collisions, like here 1 collides with 3, 2 collides with 4, and 3 collides with 4, again they will not be independent. But otherwise, they will be independent. So non-independent, if only if they are being connected by sequence collisions. This is one of the kind of the intuition that we have with the picture. Okay, so now let's put these together. Like what is the thing that we want to eliminate? What is the thing that we don't want to see? Like the bad thing. The bad thing is when you have 2 particles, they collide at time t, but they are not independent before time t. Okay, that means the 2 particles 1 and 2 they are colliding, at time t. Time t moves will be this really that. For this one, right at time t. Okay, so this is 1 and 2. They're colliding at time t, but they're also connected by sequence of collisions before time t. And this will create a kind of a cycle or a loop kind of in this whole picture. Like 1 collides with 2, 1 collides with 3, they intersect, and 3 collides with 4, 4 collides with 2. You get a kind of cycle in this picture. So if 2 particles they collide and they are not independent before, which means they have they're being connected by collisions, then this way will lead to a cycle, or what we may call the recollisions. And basically, the idea is we want to show that the probability that this recollision happen is negligible. It vanishes in the limit. And if you show this, then basically we'll see that 2 particles that collide will, with high probability, they will be independent before the time of collisions. So then you can apply these kind of arguments. And then of course, once you apply this kind of argument, you can get to this post. Okay, so any questions? So now we can summarize what we have so far. Peak collisions are essentially correspond to the cycles in the collision diagram. So such diagram, we'll give it a name, we'll call it molecules, but that's something we'll introduce later on. But essentially, these recollision horizontal cycles in these collision diagrams, the goal is to prove the probability of recollisions should go to 0. It's less than epsilon to the 0 plus, of course, in the limit of epsilon. Okay, so this is essentially the preparations that we need for the proof. And now we'll start from the short time theory. So there is a Chinese saying that if you need to go 1,000 miles, you have to start from the first step. Because of this, in order to talk about the long time theory, we start with short time. That's the key. Much less than 1. Now, the thing you do in short time theory is that you simply do expansions. Okay, so you do a single expansion starting from time 0, and then this smallness of time will guarantee that this expansion will be convergent. So you do expansions. Of course, the expansion, there are multiple ways to do this expansion. You could use this BBG hierarchy, but the things that we find more, more suitable for us is to do this expansion based on this collision diagram, what we call molecules. Okay, so based on this collision diagrams for molecules. Okay, so I'll not write down the formal definition of this diagram. Just think you have a this is a this kind of node, or you call it atom, represents a collision, and these p's represent the linear p's of a particle before each collision and after each collision. So there is a linear piece here. I mean, it's not really linear, like drawing this way, but think of it as linear. Okay, and then you have this linear piece, and it collides again with the next collision, and so on. Okay, so let me draw another example, a few other examples of these collision diagrams. Molecule. So this is why I'm wanting to use this these color chunks. If you have a okay, so the same color represents the trajectory of the same particle. So let's call this is number 1, particle number 1 here. Actually, let's call this is particle number 1. This blue is particle number 1, and then number 1, this is number 1. And actually, this green is particle number 2. And then this red, so this yellow is particle number 3. And then this red is particle number 4. Okay, so this molecule really means that there is this collision between number 1 and number 4. Okay, and number 4 goes away, and then number 1 comes on to collide with number 3. Okay, and number 3 goes away, and then 1 continue to collide with number 2, and number 2 goes away, and then with this velocity, and number 1 goes over this velocity. Okay, so this way we can write it as 1 collides with 4, and then 1 collides with 3, and then 1 collides. Okay, so this is an example of a collision diagram, or you call molecule. And then, of course, there is another example, and this one has no recollisions. You see that there is no loops, in this diagram. And there is another one. And draw it this way. So see, because we'll be working a lot with these kind of molecules in all the subsequent lectures, so we can try to first kind of get familiarized with these notions. There is okay. So again, let's call this 1. This is number 2. 2. And this is number 3. And in this picture, what we have is that you see first 1 collides with 3. And then okay, so 1 so and then 3, 3 collides with 2. And then 3 goes this way, but then 2 proceeds to collide with 1. Yeah. Now this is a triangle here. So this is the case with 3. Okay, so since we're calculating the probability, okay, so let's calculate what happens with the probability of these 2 pictures, and we'll see that why this thing does not vanish in the limit, this thing goes to constant, while this thing goes to 0 in the limit. Probability 1. Okay, so probability 1 of 1, so of the molecule 1. Okay, so this is clear because you see how many variables you have. You have the inputs, basically the starting velocities and positions, actually Vj, which equals Cj. So for the particle 1, 2, 3, 4. So there are four variables. Yes.
Do you think this is something like exhaustive, or for example, in the second example, could you switch 2 and 3 for the least important?
This is just example. There are, of course, there are many different examples with different forms of collision. Even with the triangle, you can have different assignments of these particle trajectories, and they are different, lead to different formulas. But what I want to show is that every term here is going to 0. Okay. Does it answer the question?
So if, for example, those that are able differently, you assume that they have no they have no dependence in between the first and last time.
If
for example, in the first.
If they are labeled differently, you get different terms, different contributions. But my point is that each one of these contributions is going to 0. And of course, you'll need to control the total number of contributions, and there is a combinatorial argument there. Okay, yes.
I'm not sure where you stop and stop the load. For instance, why shouldn't I care about what happens to 3 later? Or maybe you can take you said that 3 moments will interact with everybody. It is a completely I'm not sure how big the molecules are.
Okay, so this is
everything you keep track of everything that's connected to this.
So this is just one example. Like we are caring about only this part, which only has 3 particles and 3 collisions. Okay, because think of you are measuring the density of one particle, particle number 1, and we calculate the collision history of this particle 1. And let's say how many particles are involved in this collision. This is just an example where you only have 3 particles involved in this collision.
Okay, so you just care about 1 in that particular molecule, you care about 1. If you care about 3, you would give me a different answer, or you would.
I mean, we fix our, because you see we are calculating this one particle density. We fix our particle here. This 1 is fixed, and then there are of course I'll say this, and then there are of course these other particles coming in, number 2, number 3. Okay, so we are in the beginning, we are fixing the particle we're caring about, which is 1. Okay. Okay. So the probability, let's say probability of 1. So again, here we fix this particle 1. There are kind of other particles 2, 3, 4 coming in. Okay, let's see. Probability 1 is like so every factor n plus 3. Because as I just said, we fix this particle here. This particle is fixed, and this particle can be arbitrary, one of these other n particles. And this particle 3 again can be one of these other n particles, and particle 4 can be one of these n particles. So each of these particles, they are not fixed, they are arbitrary, and it gives you these n choices. And since you are fixing this particle 1 and having particles 2, 3, 4 coming in, you're getting n to the third choices. Okay. Now let's fix this n to the third, and what is the probability of these collisions? Okay. So the thing you talk about, let's say, so there is this integral of these indicator functions of all collisions. Let's say Vj. So this is the picture. So this is a combinatorial factor, the factor from the choice of particles. And this is the indicator function that all these three collisions happen. And this your product to take the integral in all the variables. Remember, since we're taking the L1 norm, all the probability we're integrating in all the actual Vj variables, including the ones you have in your density function. Okay, so how do you integrate? So let's say you fix this number 1. Okay, so fix x1 v1, which is the velocity, let's say, of this line. And then what is the condition for this collision? This collision only involves number 1 with number 4. So we integrate in x4 v4, which is this edge. Okay, then you're integrating exactly with the condition that this x and b should collide with that x and b. And that one, by the same calculation in Boltzmann's collision integral, you're getting a factor of epsilon to the d epsilon 2, let's say, epsilon 2 times the time t. Remember the time. The time is 0 and t. Okay, so fix this x and b, fix this profile. You are integrating this profile. You are having this factor epsilon squared. Now this has been fixed. Z4, x4 v4 has been fixed. And once this is fixed, then just by the collision formula, this thing has also been fixed, and this thing has also been fixed. Okay. Now we look at the x3 v3. Integrate. And now since this value, this velocity is fixed, then now when integrate x3 v3, you consider the probability that this edge collides with this edge, okay, and you get another epsilon squared. Okay, and then once you fix this, then this means that this is fixed and this is fixed. And so this edge is fixed. Again, you choose an x2 v2. In this edge, again, you integrate in x2 v2, you get another epsilon squared. Okay. So let's summarize a little bit. So the question is, you fix this particle, we call it number 1, and we consider, all the collision that happens, regarding this particle number 1 in the time interval from 0. And then let's say, there must be a number of extra particles involved in this collision. You cannot apply with yourself. So then let's say there are particles 2, 3, 4 that collides, indirectly collides with number 1 and kind of forming this diagram. Then the probability that this happens is this n-third, because each of these particles 2, 3, 4 can be arbitrary, times this integral, and this integral evaluated by first integrating x4 v4 and then x3 v3 and then x2 v3, okay, and then you get this. Together, we get probability is so Okay. You get this T to 3 because this guy is equal to 1 by the boson-Grad scaling. And T is a constant. T is a small constant, but it's a constant. It doesn't go to 0 when epsilon goes to 0. And then so you get this. So this is the probability of the case with no recursions. Okay, and now what happens with the case with recursions? For this, again, you have 3 particles. This one is fixed, so this is the particle you are studying in the beginning. You fix it, and there are 2 other particles, number 2 and number 3. Okay, and you have n to 2 times integral of collisions. And we have product J. Okay, so now let's say again we first fix this particle number 1, the position velocity of this particle number 1. Number 1. Okay, so we integrate. Fix. Now look at the integral in x3 v3. Okay. Gets to epsilon squared theta. And then we can integrate in x3 v2. And now you see the difference. Now you see once this is fixed, then this edge is fixed. Okay, and now the restriction is actually to this edge should collide with this red edge. Okay, fine. But not only that, after the collision, it should collide with the red edge, and then the outgoing velocity has to collide again with this blue edge with hardware. Okay, so this we get these extra restrictions. You think this collides with arbitrary angle, but then if you collide with arbitrary angle, it's not going to generate, it is not going to collide again with this blue edge. So then if you require this collision and followed by this collision, now this is a recollision, then you see you're going to get some probability which is much smaller than this epsilon squared. You're going to get, in fact, generically, you're going to get epsilon to the square t times another epsilon. And then you see the probability of q is less than n squared, m squared t to the square epsilon, which is t squared epsilon, which now goes 0 in limit when epsilon is. Okay, so this is the difference, the picture between the difference between the no recollision case and the recollision case. And in a short time, you simply do this expansion kind of all the way to infinity, because you have a factor of t and t is very small, so it's a power series in t that is convergent. Just say here that so we've got in short time prove takes 1, consider the collision history of it if there exists m collisions and without recollision is as you have this picture and you have m, you're going to have a t to the n minus 1. Okay, so probability of this it's big M. This we call a molecule. This is a big M. It's less than, it's equal to actually P to the M as well. Okay, so this is saying picture one. Now, if exists M collisions with recollision, then the probability is only less than Q to M minus 1 times epsilon. And that's it. When you sum up in the order M, since T is much less than 1, this sum is going to be convergent. And those terms without recollision will converge to constants, okay? And then you compare these terms term by term to the Duhamel expansion of Boltzmann, and you get this thing converges to both. And this thing converges to 0. Again, you have a factor of epsilon, so this vanishes. And then when summing n, it doesn't matter because you still have this convergent factor T less than 2. Okay, and this completes the proof in the front case. Okay. Any questions? Yes.
What is the probabilities of collision will depend on the speed of what?
There is an integral in the velocity that includes the speed. Is this what you want to ask?
But, my intuition is that if particular one is if one is large, maybe it has greater probability to collide with other particles.
You have that's why you have this integral like you have this integral in x1 v1, like you are fixing x1 v1. You think everything is in the bounded domain, like bounded by O1, so you're fixing this. I mean, if you have a v1 very, very large, but then that will have a tiny density because your density is supposed to be at infinity, then it doesn't matter. So think of this as fixed.
Okay.
Okay.
For the second case, there's some small angular approximation that results in extra epsilon.
This is just because you have this extra restriction. Not only this has to collide with this, but after this, it has to collide with this again. So this is, I mean, think of there are two tubes. Like each tube has this volume epsilon, epsilon square. But then in the section of these two tubes, it's generically going to have volume epsilon to the third. Okay. Okay. So
sorry. There is a question by Professor Livermore.
Yes.
Please.
Yeah, I just want to clarify. So far, this is Lanford, right?
Yeah, this short time, yeah.
Yeah, exactly. Okay, just clarifying. Thank you.
Okay. Okay, so this is the short time case, and now let's proceed to the long time case. Okay, now we consider the time t bigger than 1. The obvious issue is that you can no longer do the same expansion because you're going to have a factor of t to the m, and sum of this will be infinity. So how to do? The natural thing is to say that you divide your time interval from 0 to t into these short time intervals of length tau. This is okay. So this L is really large number. And then you try to propagate sign from 0 and to tau, from 2 tau to tau 2 tau 2 tau 3 times. Okay, so then we fix now, so that if we have each each interval is a short interval, and if we expand for each L, the Boltzmann solution on L minus 1 tau, L tau can be expanded as power series, at time L minus 1. Okay, so basically we try to go from this. In general, you have this minus 1 tau, it's L tau. Okay, we try to do this this timing. The issue, of course, is that at time 0 you have independence. Okay, at time 0 you have the exact independence. But at time tau, even at time tau, or of course at any later time, you no longer have exact independence, and then you need to find a way so that you can still continue doing this expansion. Okay, so this is the first key idea in the proof, is that we need to find something that substitute independence, and this thing is the natural thing to do this is to consider this so-called cumulative expansion. So for the issue, no independence at L tau, the method is to do this cumulative expansion. So let me write down what is cumulative expansion. So this is actually not a full version of cumulative expansion. It's a version, it's convenient version that we find most simplest and most useful. That is okay, remember this is S particle marginal. In the independent case, it will be completely factorized into a function of Z1, function of Z2, function of Zs. But now we don't have exact factorization. We should write it as a sum. Sum over this set H of a product J okay, so you see, this is a summation, and this part is factorized for J not in H, for particles not in H. So H, think of H as a particle set. Okay, so particle not in H, you're having this factorized thing, and this F is essentially a solution to Boltzmann equation. So in practice, it's a approximate solution, but for our purpose, for this lecture, let's just think that's solution to Boltzmann. Not exactly, but doesn't matter. So this is factorized, which means that the particles not in H are independent of each other and are independent with those particles in H.
So the index of J is from 1 to S.
1 to S.
Not in H.
Not in H, yes. Okay, and this, you see, this function depends on all these ZJs are mixed. So the particles in H are not independent of each other. So they are kind of dependent, very dependent on each other. And this term is going to be the cumulant. Okay, and actually these cumulants will be very important in subsequent proof, and it actually also provides a way to interpret how you get the time irreversible Boltzmann equation from the time reversible particle dynamics. Okay, so let's analyze. What's the behavior of this? And of okay, so first of all, because the leading term, we still think that to the at the leading term, the particles are independent. So this EH should somehow be small. Okay, so in some sense it should be small in order for our theorem to be true. Of course, we'll see that they are not small in L infinity, they are only small in L1. They behave like indicator functions supported on small singular sets. And so their L1 norm with the measure of these singular sets will be small, but their infinity norm is not small. They're kind of one on such small sets. Maybe let's look at an example, the simple example. Let's say L equals 1, L equals 0, that will vanish, L equals 1. And then you have two particles, only two particles that are not independent of each other. Let's say, what does these cumulant kind of look like? Let's see. So. So we have a cumulant containing two particles at time L tau, at time tau. Okay, so when are these two particles not independent of each other? As I said earlier, this non-independence happens when two particles are colliding directly on the time interval 0 tau, or they are kind of related by sequence of collisions. So let's say E2 tau Z1 Z2. So there is a first term in the expansion in the cumulant that is essentially the indicator function of let me use this to denote that one collides with two. Direct collides with two on the interval 0 tau. Okay, so this is an indicator function. Okay, so it's one if these two velocities collide on 0 tau, a 0 otherwise. Okay, there are other terms like not only when they are directly colliding, they can be related by sequence collisions. For example, they are when Z1 collides with Z3, Z3 collides with Z2. And then there is an integral of one collides with 3 and 3 collides with 2. Again, in this interval 0. Okay, so for example, this would correspond to a diagram. This is like okay, let me draw the okay. This term will correspond to one. This is 2. And this case essentially corresponds to have a 1. And there is a 3. And then 3 collides with 2. Let's say there's 2. This is 1. This is 3. This is 2. Okay, in any case, we have these cumulants when these particles, the trajectory of these particles are connected, no matter direct connected or indirect connected, but they're connected. Okay, essentially this is kind of the behavior of this cumulant. So what do we conclude from these formulas? First of all, they are the leading term is indicator function, so it's not uniformly small. They are kind of essentially some indicator function small, supporting on small and singular sets. And second, this cumulant itself is going to have an expansion, and this expansion is exactly based on this collision history that you see. Like how can one be connected to two? A direct collision is the simplest case. And then there is the next case is one more collision, via one thing in between, one with three with two. And then you can have, with two things in between, one collides with three, two collides with four, three collides with four. So there are these other terms. One collides with three, two collides with four, three collides with four, and these three, these4, and so on. Okay. You see, these equivalent, they themselves can be expanded in terms of these collision diagrams, or we call molecules. Okay, so essentially, let's schematically write this way. This is still the formula. Then we have and okay. So this M is an abstract molecule. That's in the case of two particles, it's something like this. And in the case of many particles, it's more complicated molecules. And this is expression. So M equals molecule. And this molecule, of course, since we are considering the equivalence at time tau, so these molecules has a lower bound 0 and upper bound tau. Let's say, and then IM, essentially the probability density for M. And basically think of this way. So there is these molecules, and there are these particles. So these represent the particle trajectory. We're calling it particle line. Basically, since we are looking at the equivalence between two fixed particles, Z1, Z2, we're basically fixing these particle lines, these particles, and these other particles. Just for terminology, we are calling these number 1 and number 2. These things occur in equivalence. These are the root particles. These are roots. And then in this, in the expression IM, you are simply integrating in all the non-root particles. Remember, you're integrating these numbers 3 is non-root, so you're integrating in 3. Okay, if you have number 4 there, you're integrating in the 3, 4, which are non-root.
So when you write characteristic function of one collides 2, you assume that there are none of the two at other collisions between 0 and tau.
This just means that this linear trajectory of 1 collides with this linear trajectory of 2, and that's it. It's a it's a linear expression, like x1 minus x2 minus tv1 minus v2. Take the inf of t. This thing less than epsilon. Okay, so they're only this. Okay. Is it one question?
Like if in addition to the other collisions, but you bound it by.
Yeah, if you can bound it, but for now, let's consider the simplest case. We only have this. I mean, there are, okay, if there are other particles, then you would introduce other particles. For now, we only have these two particles. That means we just consider the it's explicit expression defined by this. Okay. Okay, so then we write this equivalent is going to be the summation over these molecules in the first layer of this integral expression IM depend defined by its molecule, and this is a kind of heuristic answer. Okay, so now this is for the first nonlinear time first iteration time tau. Now we need to get to time 2 tau, 3 tau, and higher tau. And how to do this? You would think if you have time, sorry, this time tau, this time tau. Now, if you want to get time L tau, you want to directly do an expansion of molecule M that is really like the whole molecule between time 0 and L tau. But this will not work. We need to be careful because we cannot, since L tau is large, we cannot do a single expansion from 0 directly to L tau. It's not going to work. It's not going to be convergent. So what we do is that we really need to go from 0 to tau, and then to 2 tau, and then to 3 tau, and so on. That means we are assuming there is a formula for this form and of this form in L minus 1 tau, and then we try to derive the same formula for L. So this is an inductive kind of argument. Okay, so let's this erase this here. First ingredients. Prove that this M is a layered molecule because at time 0 to tau you have a molecule. At time tau 2 tau you have another molecule. You're going to join these together to get a molecule between 0 and 2 tau formally. And then after L tau you have these L submolecules, and we join them together to get a big molecule, which we call these layered molecules. And again, IM is expression integral defined by M. Okay. So this is basically the first half of the first main ingredient of the proof. We're going to do an induction in L to prove this one. Okay. So before we proceed, let's look at the case if we choose L equals 1, you get this formula at time tau, and you want to get to time 2. Okay, so let's say we have these 0 and tau and 2. Okay, so there is something here. Now, basically, this thing described, once you know the knowledge of this EH, knowledge of this M, of this I, you have basically a complete description of this ensemble at time tau. Okay, so this ensemble at time tau. Okay, so you want to go from tau to 2 tau. So there's a question here. Like, what if you try to go back from tau to 0? Because if you're given this ensemble at time tau, and then if you go forward or backward, since the Hahn-Sphere system is time reversible, if you go forward versus going backward, you're just switching the signs of the velocity. Okay, but then how come you get two different equations going from this way? You get a Boltzmann equation at time 2 tau, and going this way, you get a Boltzmann loop at time 0. How come you get two different limits when you go forward and when you go backwards? So this is a question of how do you see the time irreversibility of Boltzmann starting from this time reversible, Hahn-Sphere dynamics. The answer is exactly because of this ensemble at time tau. Remember, this ensemble is to the top order is independent, but you're going to have these cumulative terms. Okay, if you have this cumulative term, it's precisely these cumulative terms that creates a difference between going forward and going backwards. So let's look at one example, you're going to see it. Okay, so time irreversibility. Assume we go from tau to 2 tau. remember at time tau the ensemble contain, if at time tau everything was exactly independent, then there would not be any difference between going from tau to tau and going from tau to 0. And now since you are having these cumulant terms, the cumulant d2, let's say tau d1, d2, let's take the first first order term expansion, which is indicator function of this z1 applied to z2 in interval from 0. Okay, so this is what? This is basically the indicator function of if v 0 tau, and then we have x1 minus x2 minus t v1 by v2. That's an apple. Something like this. Yes, actually x1 minus t minus plus t. Same. v1 and v2. Let's say this way, okay, just for illustration. Okay, so if you consider this indicator function and evolve forward tau to 2 tau, and then let's say you have a collision, that this at time 2 tau have particle 1, that's a collision, so particle 1, it's 1, it's 2, it's 2. Okay, and then to backtrack to to expand based on the data in the time tau, you're going to see this initial ensemble at time tau, and then if you see this cumulant term, okay, if you see this cumulant term, the contribution of d2 is basically the integral of the indicator function of z1 applied to z2 in tau 2 tau and the indicator function of z1 applied to z2 in 0 tau. Okay, because this collision happens between tau and 2 tau. Okay, and the indicator function coming from the cumulant is really saying that this collision happens in 0 tau. And these are two disjoint time intervals. So these two conditions, they are one and not exactly independent, but the probability that both happens is tiny compared to probability were individual. Okay, so this means that if you go from tau to 2 tau, then the contribution of this E2 is negligible. If you go from tau to 2. However, if you go from tau back to 0, that means you have this tau, and going back to 0. Okay, so there is another condition here, but this just means that contribution d2 is going to be integral of indicator function z1 applied to z2, now also in 0 tau, times this factor, which is the same factor as you see in E2, again 0 tau. And this is not small because these two indicator functions have same indicator function. You're just integrating one indicator function, and this term is not going to be small. It's going to have unit size. Okay, I mean, of course, with a normalized constant. Okay, so let me summarize that it is precisely these cumulants that allows you to distinguish this direction of time of going forward and going back. Okay. Now with this, we can proceed to talk about the proof of this form. Okay, so as I said, we proved this by induction. I'm only going to show you the schematic way to see how do you get some, how do you derive the formula for Fs from the formula for EH, and how do you get the formula for EH, from the formula for previous times. I'm not going to write down this whole big integral formula. It's going to be too big, but I'll show you kind of schematically how this works. Okay, so my visibility. And of course, I'm going to show you what is this molecule M, and what is this I of M? Group. So F was 0, everything is trivial, because there is no cumulant, F, the cumulant 0. Trivial, and then DH is 0 for non-empty H. Now let's assume this thing is true for elements. So by the way, so here we are in this description, this formula, we're already making a number of simplifications. In fact, in the real proof, we need to perform a truncation on each level, on each layer between L minus 1 tau and L tau. That restrict the number of particles. You can see the number of clustering particles you can see, and the number of recollisions you can have. But just for simplicity of presentation, let us ignore these issues for now. Okay, so assume true for L minus 1. Then what do we do? Okay, so let us say that if we start from L tau, L tau with S particles, working with S particles, we want to ZS. Let us call them the root particles. This is a root particle precisely of layer L. Because we are doing induction, so there will be root particles of layer L minus 1 and so on. So these are the root particles. And what we do, we're going to do the expansion. We are considering all the collisions that involve one of these root particles. For collisions that do not involve any of the root particles, or kind of not even indirectly related to these root particles, they don't matter in the dynamic, in the distribution of these C1Cs. Okay, so we consider all the collisions that directly or indirectly involve a root particle. And we get the molecule ML in layer L. So this layer means that L minus 1 tau for L. Okay, so we have a molecule here. Schematically, let's draw it. Tau, and we have a bunch of let's say the root particles here. So these are essentially the root particles. Give the name of R and L. And these particles are going to have collisions. They're going to have collisions between themselves. Okay, so maybe they'll be this, and they're going to have collisions with other particles. Let's say they're going to have collisions with other particles. Okay, but these particles also count in the molecule in the layer L, and there are others. So whatever you want, there are others, and there maybe have to divide them. But whenever you're having a molecule and you have L minus 1. Okay. Now at this time, you're going to see that given this collision, diagram or kind of molecule M, you're going to have this Fs is so right here. So Fs of Z1 to Zs. Now, if you consider all those particles going down, that occurs here. So there are these particles that you see at this time L minus 1 tau. The number of particles is larger than S because all those S particles, you're seeing it here, but there are also the particles that are not originally root particles that just occur, kind of get inserted in this molecule, they also come here. So here in total, you're going to have this S plus, so S plus bigger than S particles. Okay, so if those S plus particles get measured at this time L-1. Okay, and then so the Fs is a sum in M. Okay, once you fix this molecule M, we'll have the integral expression involving this Fs plus L-1 tau, W1 Ws plus. Well, W1 and Ws plus are basically the initial configurations of these S plus particles at L-1. Okay, so now we're going to plug in the induction hypothesis, which is this. Sum in M, sum in H prime, which is a subset of 1 to S plus, and then you have a product of F L-1 tau Wj, J not in H prime, okay, and then we times this E H prime L-1 tau Wj, J in H prime. Okay, so forget about this formula, just look at the picture. So in picture, we have these total S plus particles, and then we're going to have a subset H prime of these S plus particles. So in the picture, let us assume those particles that are not in S prime, we don't allow it to cross this time interval. We just draw it like this. This one I draw like this. But for those particles that belong to this H prime, we allow them to cross. Okay, so of course there may be others allow them to cross, and then maybe there are some other things that they gets crossed. So whatever, like because of this. Okay, what does this mean? So these reds are the root particles. Red R of M L-1 is the root particles at L-1. So why is this? Remember, what are these root particles? These root particles are those particles you see when you're dealing with this Fs. Let's say if you later on are going to reduce to the cumulants term, but essentially these things are, think of these things are the root particles in the whole S, particle marginal, or the cumulants. Later on we'll see. Now these reds are exactly those particles that you see in these cumulants. As L-1. So in other words, among all these S plus particles, for the non-red particles, these white particles, you're going to have factorized at L-1. Now we directly already get this solution of Boltzmann, which you know very much knowledge about, so don't need to further expand them. But the thing you don't know is this cumulant thing at L-1 tau. So for corresponding to these red particles, so if you have red particles, you should further expand their history into the time before L-1 tau, presumably between L-1 tau and L-2 tau. Okay, and because of this, you're going to see these are new root particles that you are going to see the expansion by induction hypothesis. Remember, this EH prime is a sum over this M prime. Okay, M prime is a molecule kind of everything down there from L-1 tau to 0. Okay, so this thing is M. Okay, and then once you have this M prime, which occurs in the induction hypothesis, and then you have this layer particle ML, you simply put this together to get a kind of overall particle, M prime overall particle is M. Okay, let me write it in this way. And Fs is equal to sum. This is ML, ML, and sum over M prime and then of this integral expression involving these Boltzmann solutions f minus 1 tau, and then we have this EH prime, and EH prime is expanding into the I of M. Okay, so this is a bit abstract, but just look at the sum. You sum over ML and you sum over M prime, and of course, M prime is supposed to have a set of root particles, and these root particles is exactly this H prime set. Was that what you have here? Of course, this H prime is arbitrary, which corresponds to the fact you're having a ML molecule L in this level, and M prime which is arbitrary.
Excuse me, can you explain again why you extend some of the branches? What is the reason why you need to extend some branches, but maybe not all of them? Below L minus 1 tau.
The reason is that you have these particles, and each of these particles is evaluated at time L minus 1 tau. However, you have this expansion in L minus 1 tau. Some of the particles fall into this factorized thing. If they fall into this factorized thing, you already know their behavior. Their distribution at L minus 1 tau is given by the Boltzmann solution. You don't care about it. No, you don't care about it. You don't need to, further expand it. But there are those particles that belong to the Cunan thing at L minus 1 tau. And for those Cunan thing, you need to further expand it in order to get a formula for the Cunan. Okay? And Cunan will get you this I of M prime, where M prime is a molecule between L minus 1 tau and 0, and ML is molecule between L minus 1 tau and L tau, and put together, you get a molecule overall, which is just M. And then, of course, M of this integral expression, let me write as I. Okay, so of course this IM involves this subsequent integrals. So I prime itself is integral, and you from this integral you add in those tensorized things of Boltzmann solution at L minus 1 tau, and you get a big integral. Okay, we'll see the exact expression of IM, but these are basically can be constructed, in that. Okay, so one last thing. Remember, our goal is to show the expansion formula for the cumulant, but this is not a cumulant. This is the full kind of S-point marginal. So how to get to cumulant? The answer is easy, because you just think of this M. Remember, we want to find from this marginal, S-point marginal, we want to find things that can be factorized, and things that cannot be factorized are cumulants. Okay, what are the things that can be factorized? And the answer is easy. Basically, you think this molecule are drawing as connected, but in general it may not be connected. And the part that is not connected, let's see. One last point in I of M. If M has a connected component, let's say, really ML has connected component, where you have only one blue, okay, whatever you do, and no red, with one blue, and no red. What does this mean? This means that, first of all, there is only one blue, which means this particle is not talking to any other particles, any other root particles in this layer, because there is no collision. They are not in the same connected component. And then we have no red, which means that this particle is also not talking to other particles indirectly via earlier layers. Because if you have red, and all the red are correlated, they are not independent, then it may be kind of indirectly talking to other particles in other layers. But if this component has only one blue and no red, then this part this thing is completely factorized. Okay, so this intuition, like if of course if you have other particles like this, they may be connected to other particles, but then this you cannot factorize, they are connected. Or if you have other particles that are not, but eventually you get a red, then you can still need to expand further into the earlier layers, and you don't see it. You don't see this factorization. Only here you see factorization. Okay? Then we can factorize. And the factorizing, remember, if you have no red, remember the white ones correspond to the Boltzmann solution at time L-1. So if this component has only one blue and no red, which means that all these inputs at L-1 are exactly Boltzmann solutions, then what happens? You're essentially just having this part with input being L-1 tau with data of Boltzmann solution L-1 tau, and do these three expansions. Okay, then the short time theory will tell you that whatever you get out here is exactly the solution to the Boltzmann equation at time L. Okay, remember there is no current here, so you're not going to track to the early layers. You only look at this L-1. So this is essentially a short time theory. So we don't worry about these things. If you have a kinetic component, this molecule here has only one blue and no red. So otherwise, what are you considering? Or considering those kinetic components with either at least two blues or at least with one red. So then we can factorize those. And then this is equal to, H1 to S. Well, what is A? Here this H is a set of root particles where you have a component like this. If you have a component like this, then this will be factorized. Okay, and in factorized term, if you are sorry, so H, the common H is those factorized. So N and H. And what is EH? EH is just this. EH is just that all the components that contain at least two blue or at least one red. So let me summarize. This is L tau. There is a blue things there. Okay, so maybe you're going to see this. I don't know. This, okay. And there is a blue here. Have this blue here, whatever. And they may or may not be connected, and then you're going to see some red. Maybe you have some red. Okay, so maybe these are not red, and these are red. Okay, so thinking is that the blue equals the roots at L tau, red equals roots at L-1 tau, and then the Kuhn condition we just described here ensures that each component, this is ML, either contains two blue or contains one or more than one, of course, one red. And of course, this is the layer L particle, and then you have this layer L-1 coming from induction hypothesis, L-2, L-3, L-4, and so on. And finally, you're going to get this homework. And finally, L is constructed. So the whole module M constructed from ML and L-1 up to M1. And each layer you're going to satisfy these key properties. Of course, when you look at this ML, this is the blue and this is the red. But then when you look at the earlier layers, the red will play the role of blue, and then you have some maybe green will play the role of red, and we'll keep going to the previous layer and so on. So this is a molecule M that we see in the picture, we'll see that this fact is a fundamental property of the molecule that guarantees, why our expansion is going to be convergent. So this may we'll talk about next time. And one last thing about what is expressed for IM. I promise to say the definition of M and definition of IM. Now this definition of M, okay, you can draw draw whatever, combine with whatever M-1, M-2, and so on, whatever M you get. And IM is essentially basically just IM is density that all collisions in M happen. So actually in practice, we're going to measure the IM in L1 because L1 normally we're really, interested in, and then the IM L1 is the probability, normalized probability. Normalized means you are multiplying by a number of factors of n because you have all these free particles that can be chosen from one of the n particles. But it's normalized probability of collisions in M happen. So there is a more concrete expression I will write down in the next time. It's a huge integral involving all the atoms and all the edges in the molecule in all layers. It's too long to write them now, but I think this is clear enough. So the normalization you don't need to worry about. It's always a correct half, and I think it's the probability of the collisions in M happen. Like what is probability that there is collision here, there is collision there, there is collision here. It's an integral over all the initial configurations of all the particles involved in this whole molecule. But in any case, we get an expression. So now this, you agree this is an inductive proof. Like if you have L-1 tau, then by going through all these complicated arguments, you get to this result at L tau, and you complete the inductive proof. And now the next thing that remains, the only thing that remains, is to show so goal for next time is to bound the number of molecules. And this is an easy task. It's a counting number of trees, so it's easy. And then to bound IM in L1 probability for individual. And this, of course, is hardest part. We'll need to first get an expression for this L1 norm. We'll see the expression involving the integrals in all edges and with a huge number of delta functions. And then once we have this formula, we're going to find a way to estimate this formula. And this is going to be done by estimated by a combinatorial algorithm called cutting. We use, of course, cutting next time. And then once we know how to do the cutting, we get a way to estimate this integral by just reducing the iterate integrals using Fubini. And then we need an algorithm to do cutting kind of effectively. Okay, so this will leave for next time. So next time we'll start with this expression. I'll write an expression, I'll explain what it means, and then how do we do the cutting, and then the algorithm will take, I hope it will occupy most of the next section. Yeah.
Thank you. Do you have some questions for you? Visually.
Your formula for iodine in L1 norm,
Yes.
is it going to are you going to be composed to use this equation MN and then -1 and 1? Are you going, is it going to be a sum of functions from MN for MN minus 1 until N1?
So it's a big integral that involves all the nodes or atoms in every layer, ML, L minus 1, L1. So M is a kind of a union, a combination of each of these. So this enters into this, and there is this further atoms in the L minus 1 layer, and so on. So it is in big integral involving all these different ingredients from all these different layers.
So,
No, it's not a sum, it's an integral. There is no sum. So for each fixed M, it's just an integral. So we're of course we are summing over different M. But for each fixed M, it's an integral.
integral, but it's, this integral is not, I cannot say that for each pixel, the integral is the sum of your sequence of integrals.
No. So okay, so there is no sum in L. It's just like M contains a part of here, ML, a part of ML minus 1. So it's a big integral formed by small integrals, but then you will see that the expression IM is really just integral in all the. Let me just say so. So this is, it has 3 layers, and then we have whatever collision and go down here, and then maybe go down here. Okay, but this is the thing. So you see the integral is really just integral in all the, for each collision you have a time variable. For each edge you have vector variables Zj, Zj there, and there's a Tj here, and you're integrating all these Zj variables, integrating on these time variables, various delta functions, and basically the thing you see from different layers is that this time Tj, if you have this time Tj, this is 0 and tau, then this Tj must belong to 0 and tau in this collision, and next collision this time must belong to tau and 2 tau, and so on. So this is where you see the different layers.
Thank you. There is a question at distance by Professor Livermore.
Yes.
Please, Dave.
Yeah, could you say a word about where your analysis, as you've covered it so far, differs from, say, Illner-Polverenti or any other analysis from before?
Well, the thing is that they only consider one layer, right? So they are, for example, let's say, let's take the paper of Polverenti and Séminaire in 2016. Okay, what they do, they're considering one single layer, okay, and they're assuming the initial data being, well, not exactly independent, but with the cumulants being small in L infinity. And then they conclude that the cumulant at later time, at time tau, is going to be small in L1. Okay, this is fine. But then in any case, they're dealing with only one single layers. The main difficulty here is that you really need to deal with multiple layers. So actually, even if you just look at 2 layers, of course, you are not supposed to use the fact that 2 tau is small. If you really look into analysis of going from 0 to tau and tau to 2 tau, if you only consider 2 layers, you're already seeing a lot of difficulties that is not seen in the one layer. For example, this proof of Polverenti and Séminaire is not going to be inductive because they assume smallness L infinity and it derives smallness in L1, and this cannot be propagated.
Okay, thank you, Benoit. Oui.
Can you say where you use the smoothness of the Boltzmann of the solution of the Boltzmann equation? Where does it enter?
The Boltzmann equation is Boltzmann solution is not small. You mean the time is small? How is small? Smoothness. Okay. It doesn't really have to be smooth. It has to be uniformly bounded with decay in V, fine, but it really doesn't really have to be smooth. Like the smooth has to do with the
Where do you use it?
It used in, remember we have this completely factorized thing that has only the Boltzmann inputs, and then you have all these red things with only one pool. Okay, so this gives you have a Boltzmann expansion, and this is essentially the short-time theory. And in the short-time theory, if you want to start from the approximate Boltzmann, go to the next approximate Boltzmann, you need some kind of stability. And for us, the simplest way to show the stability is to take a little bit of the derivatives, allow a little bit of smoothness of the solution, and that's it. So it's really like we don't need to lose one derivative. We can lose, for example, like any one lower 10 derivative, any small amount of derivative. So it's really not the smoothness that matters. It's really the decay in V that matters.
Thank you again. Is there any additional question? At this time?
Yeah,
Yes,
I have one, if more. Sorry, I didn't see, maybe you could discuss what's the difference of doing it in the whole space in which there's, for a finite representation, there's only a finite number of collisions, or doing it in the periodic box. You raised this differences on Friday, but you said nothing about it today. Has it entered the analysis yet?
Okay, so there is almost no difference. Basically, the only difference comes from the fact that in the whole space, if you have a finite number of particles, you have absolute upper bound on number of collisions. In the torus, you don't have this, but you can have something substituting it. We giving the probability of too many collisions is small. You can show it's sufficiently small, but that's the only technical difference. And otherwise, in the expansion, there is no difference. And in the estimate, in most part, there is no difference. Only one part, which I'm not even mentioning, which comes from the case where you need to truncate the number of recollisions. If you have so many recollisions in one single layer, you need to prove that this has tiny probability. And in that particular proof, you are using this theorem of Burgo and collaborators on the upper bound of collisions that holds in RD. And in the torus, you need to do something slightly harder to get. But it's really not really in the main thread of proof. So I'm not talking about it too much.
Thank you.
okay, thank you very much. You